Hello, everybody. So now we are going to discuss the second type of problems that we will go through in this part of the turbulent flow and the losses in case of turbulent flow. So let me just go back to the slide where we discussed the different types of problems, and we discussed already this type last time, and we saw that this is a type of problems that we can solve directly, so we don't need to go through long procedure. We just follow the normal procedure. We calculate epsilon over d, then Reynolds number, and then friction factor, and then the losses. So it's straightforward solution. Now we are going to discuss the second type, where we have different givens and different requirements or something that we want to calculate. Here we will need to calculate the volumetric flow rate, the velocity, or the mass flow rate. And we are given the length, the diameter, and delta P or the losses, whatever any of them. So let's see how we can deal with such problems. So in this problem we have an oil tank that contains the oil. We know the density of the oil, the kinematic viscosity, and from them we can get the viscosity of the fluid. And it is discharged in 50 millimeter diameter pipe, and 40 meter long. So this is these are the dimensions of the pipe, and this pipe is made of cast iron. If we go back to check what this cast iron will mean, we can check in here. So cast iron is has a roughness of 0.26 millimeters. So this is what we make out of this, or the information that we understand from this, that we know the roughness of the pipe, and we are given information here. This is important, that it's a large diameter tank and it's open to the atmosphere. So we know this means that the velocity of the surface of the fluid is going to be 0, and the pressure is atmospheric. It doesn't mention anything, the problem statement doesn't mention anything about the pressure on the outlet of the pipe, but it's clear in the figure that it's open to the atmosphere as well. So the pressures are equal. Sorry. And the height of the liquid is 4 meters above the pipe. And we want to calculate the mass and the volumetric flow rate of the oil through the pipe. So we want to know how fast the oil is flowing through the pipe. So this is the summary of the givens that we have. So again, I like to start with the very basic principles, which is Bernoulli equation. So we apply, and then we will see how the velocity can be calculated. So if we apply Bernoulli equation between the surface of the tank and the effluent of the pipe, then we have 0 velocity at point 1. The height is 4 meters. This is atmospheric. Here is atmospheric. The height is 0 and the velocity is unknown. And of course there is no pump and there is no turbine, so the equation will reduce to Z1 equals U2 square over 2G plus HL. And this losses is FL over du square over 2G. So we have U2 square over 2G and U square over 2G, so it's going to be U square over 2G as a common factor, multiplied 1 plus FL over D. So now if we want to, we can substitute, of course. So we can substitute with the length, with the diameter, and with Z1. So from this we can get a relation between U and the friction factor. And here comes the problem. So we know that the friction factor is calculated from Reynolds number and epsilon over d. So we know Reynolds number, it's rho u d over mu, and we know the density, the diameter, and the viscosity, but we don't know the velocity. So it's going to be function of velocity as well. And epsilon over d is already known. And based on this we will notice something that is something new that we haven't seen before. We want to calculate the velocity, and for calculating the velocity we need to know the friction factor. So if we know the friction factor, we can calculate the velocity. And to calculate the friction factor we need to find Reynolds number, but we'll see that Reynolds number is function of the velocity as well. So we are kind of in a closed loop that we need to know Reynolds number to calculate friction factor, so that we can calculate the velocity, but Reynolds number is also function of the velocity. So each one of them is dependent on the other, which makes it an infinite loop. There is no point you can start the solution from. It's not like the previous case. In the previous case, we already knew the diameter, we knew the velocity, we knew the surface roughness, so we knew all the information that we need to know so that we can calculate the Reynolds number epsilon over d, and from them we could calculate the friction factor and then the losses. But here we have this issue. So the only way we can solve this problem is by trial and error or by iterative solution, which means that this loop has to be broken somehow. So if we break the loop at one point, so we can get numbers. If I have a value of f, then I can calculate the velocity. Or if I know Reynolds number, I can calculate the friction factor and then the velocity. So this is what I mean, that if you have a number, the loop will be closed, or I mean broken. So what we do is we assume a value of any of these parameters, let's say the velocity, the friction factor, Reynolds number, and then we do the calculations. Let's say I assume a friction factor, then I can calculate the velocity, and then I calculate Reynolds number, and then I can recheck on the friction factor. So I can do a check to see if the assumption that I made was correct or not. So if it's not correct, if it's correct, then the assumed value and the calculated value will be equal. If it's not correct, then I have to redo the calculations again 2-3 more times until the assumed and the calculated values match. And this is what we call an iterative solution. Okay. So just to summarize the equations that we have a formula for Reynolds number, we have and epsilon over d, we have a formula which is from Bernoulli equation, which is the velocity as a function of the friction factor, and we have Colebrook equation or the chart. And we have two options. You can do this using the chart or with using the equation. The good thing about the equation is that we can combine more than one equation. So here, if you see this, I already substituted with epsilon over d, and here I substituted with Reynolds number. Okay, so this is already after putting the numbers that we have in the equation of Reynolds number, which is 8064.5 u. So I put it here, and this is what we have at the end. So I don't need to calculate Reynolds number because I don't need it. It's already part of the friction factor equation now. And what we are going to do is, as I said, trial and error. So we'll assume any value of epsilon over d of friction factor. And this is one important thing here, that as I said, you can assume anything. You can assume Reynolds number, you can assume the velocity, or you can assume the friction factor. But to understand why I chose to assume the friction factor, we need to go back to the chart. So if you take a look at the chart, you would see the range of Reynolds number starts from 10 power 3, or if we are interested in the turbulent flow, it is from 4,000 up to 100 million. So it's a very, 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 very wide range. So assuming a value has a very high probability to be far from the actual value, which makes the conversions slower. Conversions meaning how many trials we need to take or to do until we reach the actual or the final answer or the right answer. So if you assume a value that's very far, then most probably you have to go through many iterations so that you reach the actual value. While if you look at this range of the friction factor here, you'd see it ranges from 0.008 to 0.1. which is a very, very narrow range compared to the range of Reynolds number. Okay, so this is one thing that makes the assumption of the friction factor logical. The other thing is that we calculated epsilon over d, and this is also one more advantage in this case. Epsilon over d was 0.005. So if you check 0.005, it's between 0.004 and 0.006. So it starts from 0.03 almost, and the maximum value of the friction factor for this is less than 0.05. So the friction factor will definitely lie somewhere between these two numbers. So this makes it even a narrower range. So if you assume it 0.04, you know for sure that it's very close to the actual or the right answer. So this is why I assumed it. So actually this point of knowing the range of epsilon over d, it was a suggestion from one of the students, and actually it was a very smart suggestion from him. And the actual solution that I made, I started from 0.01, which is not a good assumption. But as I told you, no matter the value you assume, it's going to be close somehow to the final answer. So from this f assumed, I calculated the velocity, which is 2.95, and from the velocity I substituted here and recalculated the friction factor. So comparing these two numbers, it started with 0.01 and ended up to be 0.036. So it's a huge difference between the two numbers. So this means that the assumption is not true. So the next assumption is the product of the first trial. So we take this number as the new assumed value, substitute here and repeat the same thing, and then you calculate the velocity is 1.6, and then the calculated value is 0.0365. So you see here the values are getting much closer than before. So the difference is only in the fourth decimal place. Again, in trial 3 and trial 4, you'd see that it reached a point where the number is already the same. So this is the answer that we got, that the velocity is 1.612 meter per second, the volumetric flow rate is 0.00316, of course multiplying the velocity by the area, and this is the mass flow rate. So this is one approach that we can do. We can make it even more quicker by combining these two equations, and this is valid only if you use the equation. If you are using to calculate the friction factor, if you are using the chart, then you have to go step by step. If you combine the equations, you'd see I put here the velocity instead of I combine the two equations. This is the velocity. Okay, so now you have one equation that is function of f, and you can do the same thing. The big advantage of this approach is that you can, as we saw before in a previous video about calculating the friction factor, you can use Excel or the goal seeking Excel to calculate the friction factor for you. So you don't have to do this table again. It will just do it in one step. But I think the calculators that are available now can solve these kind of problems as well, or equations as well. So anyways, this is an approach that you can follow. However, if I'm doing this, and this is what I'm going to show you in the next video, inshallah, that if you do this using Excel, I prefer to calculate it one by one instead of just combining the equations, because there is a big possibility, if you are not careful, that something is wrong with this equation. When you combine 2 or 3 or 4 equations together, you might put a sign in a wrong way, multiply a number with another number, which is not the right thing. So there is a possibility that the equation is not so accurate. But anyways, this is an option. You can use it if you're interested. As I told you, in the next video, inshallah, we're going to see how to do these calculations, or I'll show you how I did these calculations using Microsoft Excel. So I'll see you then, inshallah. Goodbye.